All right, welcome back. You ready to go? We are going to talk about energy some more today. If you remember in our last video, we talked about heat energy, and this time we're going to talk about the energy that is involved when chemical reactions occur. Specifically, we'll be looking at the energy when bonds are broken or bonds are formed. So we are either going to have energy that is going to go into the reaction or it's going to go out of the reaction. Endothermic means you are entering, the heat is entering the reaction. Exothermic means it is exiting. Okay? And we're going to see which one of those occurs when bonds are formed and when bonds are broken. Every reaction is going to involve both of those. If we have a chemical reaction, the reactants that are on the left side of the chemical equation, the chemical reaction, the bonds that are there have to be broken, and then those particles are rearranged and new bonds have to be formed. So bonds are broken, new bonds are formed, both have to happen in order for a chemical reaction to occur. Okay? And we can think of chemical reactions a lot like playing Legos. You have to pull apart your old the Legos that you assembled originally, okay, you put together. You have to pull those apart if you want to make something new, assuming that your Lego parts have been put together at some point. You were playing with them before, so you have to take apart your last creation and then rearrange those to make something new. That's kind of like what a chemical reaction is. And we have to break the bonds before we can put the atoms back together in order to form new bonds and new products. All right? Both processes involve energy. The net energy, okay, if both happen, one's going to be using energy, the other one's going to be releasing energy. And then the difference between those two, if you add those together, one's positive, one's negative, you bring them together, the net result is called the heat of the reaction, or the change in enthalpy. Enthalpy is just a fancy word for heat energy at a constant pressure. So when we're looking at this energy as it is related to chemical reactions. In Model 1, we have breaking and forming of bonds, and here we have a whole list of reactions, and in this column, the change in energy. So we are told we have a change in energy. It is measured in kilojoules per mole. The RXN stands for reaction. And here we have some others, and again the reaction is given to us. Again, the change in energy measured in kilojoules per mole for the reaction. Let's look at the questions. Identify 4 reactions in Model 1 where bonds are being broken. Bonds are being broken. How are we going to know? Just look at what's happening comparing the left side of the reaction to the right side. If you remember, we looked at types of reactions in the previous video, and we looked at what happens when you have a synthesis reaction or you have a decomposition. Decomposition, you are taking a single entity, a single compound, and you're breaking it apart into multiple compounds or particles or elements. Okay? That's what we're looking for here. Bonds are broken. That means you're starting with a single compound, reaction occurs, here's our arrow, our yield arrow, and we have 2 products. Well, the only way you're going to have 2 products is if something busted apart here, something broke. The bonds have been broken and these particles have been released in order to kind of create new products. So all of these here are showing us broken bonds. Bonds were broken. Bonds were broken. Bonds were broken here. Okay? They're showing us a reaction where they're kind of focusing only on a decomposition where bonds are broken. Over here, you guessed it, this is where bonds are being formed because they're focusing on a synthesis reaction. Okay? So the bonds are being formed because we're starting with elements over here. So there's nothing to break. You can't take phosphorus and break its bond because it's not bonded to anything. So you have pure phosphorus, pure chlorine, and now they're going to form bonds here after the reaction occurs. Okay? So this side is all breaking the bonds, the other side is all forming the bonds. All right, we did that, 1 and 2. Circle the correct word to complete each sentence below. When bonds are either broken or formed, there is positive energy change. Well, when they're broken, positive, 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 positive. When you see a positive energy, that means energy is going into the reaction. You've got to absorb energy. Plus means the reaction is adding energy. You have to gain energy in order for that reaction to occur. So, when bonds are broken, positive energy is needed. You have to bring energy into the system. Breaking bonds, therefore, that is endothermic. Endothermic, entering, heat is entering the system. Heat is entering the reaction. When bonds are formed, negative energy. Negative energy means that this, in order for this to occur, or when it does occur, that heat energy is released. Heat energy goes out of the system and it is released into the surroundings. That is exothermic reaction. Exiting the reaction, exiting the system. Find two reactions in Model 1 that are exact opposites of each other. That is, one reaction is the reverse of the other. And we're going to say down here, how do those changes in energy for the reverse reactions compare? And we're going to explain that as we talk about breaking of bonds and bond formation. So the idea here is, let's see if we can find two that are basically just the flip of each other. And it looks like A and E. This is phosphorus trichloride breaking apart, decomposing into just phosphorus and 3 chloride atoms, or 3 moles if you want. And here we've got phosphorus and 3 chlorine atoms synthesizing, combining into phosphorus trichloride. So these are just opposites of each other. One is going in one direction, the other is going the other direction. Just flip them over, and notice here we've got a positive heat energy, or enthalpy of reaction of 966.7. Over here it's a negative. Same magnitude but opposite direction. Plus or negative tells you direction. Positive, it's going into the system. Negative, it's going out of the system. Okay, so these are opposites of each other. And that just means that the breaking of the bond and the bond formation, they are kind of opposite processes, that the energy for breaking a bond, to break that bond, is going to be equal in magnitude but opposite to the energy to form that same bond. Okay? So the magnitudes are the same, but the sign is the opposite. So that just simply makes sense. If you want to form a bond, then a certain amount of energy is released. If you want to break that same identical bond, it's going to take the same amount of energy, but in the opposite direction. Okay? So when bonds are formed, energy is released. To break that same bond, you have to insert energy, bring energy into that, exert energy. What unit is on the energy changes? So, as mentioned up here, these are all kilojoules per mole. So it's not per bond. Remember, we don't usually talk about one atom, one compound, one molecule, one bond. We talk about huge quantities of these particles in chemistry. So this is a kilojoule per mole. Kilojoule per mole. This is how much energy. This is an energy unit, kilojoule, and this is per how much we have. We have a mole of whatever particle we're talking about. For reaction A, Model 1, how many P, that's phosphorus chlorine, PCl bonds are broken with the 966.7 kilojoules of energy? So we have to look at the units here. So what they're telling us is, if we look at reaction A, and we've got this bond, phosphorus is bonded to chlorine, but this is the energy here needed not to just break one bond, is to break a mole of these bonds. 6.022, remember this number? Times 10 to the 23rd. That's how many bonds we have of phosphorus and chlorine. So we have a sample of this compound, and it's got that many bonds, and it takes this much energy, 966.7 kilojoules, to break all of them. Calculate the energy needed to break 1 mole of PCl bonds in reaction A. So if we look here, we've got 1 mole of them. So it's going to take 966.7 kilojoules to break apart a mole per mole of the let's check up here. Is this PCl or it's PCl3? My apologies. Let's just make a small little alteration here. PCl3. All right. So actually it would be P bonded to 3 Cl's here. All right. So it's P bonded to 3 of them. Okay. So if we've got PCl3 and we broke apart PCl3 to form phosphorus and 3 chlorines, and it took that much for the reaction, for a mole of this, okay? Now it's saying, what if you just have PCl? Not PCl3. This number up here is for PCl3. Well, there are 3 bonds for every molecular unit of PCl3. So this 966.7 is how much it takes to break all 3 of these bonds in a mole of that molecule. Okay? Well, if you just want to find out what is it for just a single PCl, then we're going to take this number and divide by 3, obviously. Okay? So you're going to take your 966.7, divide that by 3, and you're going to find out what the energy needed to just break one of those bonds. Okay? Calculate the energy needed to break 1 mole of PCl bonds in reaction B, and do the PCl bonds in different molecules require the same amount of energy. Alright, so now we have the same bond, but now it's in a different reaction. So here, this time we got 5 of them. So this PCl5, how much energy does it take to break all 5 of those? Well, 1,297.9 for the entire reaction, but this time you've got 5 of these. So if you take this number, 1297.9, we had 1297.9 kilojoules per mole here, but remember this was for 5 bonds, so we have to divide this by 5. So if you take 1297.9 divided by 5 and you compare that to your 966.7 divided by 3, you're going to find that you're not getting exactly the same number. They're kind of relatively close, but it's not exactly the same number. Here we've got 5 bonds around the phosphorus, each of them with the chlorine. Up there we just had 3. And the reason why they're not going to be exactly the same numbers because there is going to be kind of some dynamic forces happening as a result of having the 5 bonds around the phosphorus instead of the 3. So there's some influences happening that kind of alter the bond energy that we calculated for these two questions. But they do differ a little bit. They're close. And so when we talk about bond energy is going to really be kind of an average if we talk about the bond energy for phosphorus and chlorine. So it's not exactly the bond energy for a particular molecule, like in PCl3 or PCl5, because they differ a little bit, but it's more of an average of all of the possible different bonds in molecules using phosphorus and chlorine. All right, that's kind of what we say here is the bond energies. The bond energy for a particular type of bond can vary from one molecule to another because the atomic environment of the bond can influence the amount of energy needed to break the bond. So a carbon-carbon bond, for example, in this molecule, here you got a carbon-carbon bond right here between those two carbons, might be the bond energy for this carbon-carbon bond is going to be different than the carbon-carbon bond here because it's surrounded by chlorines on the right side instead of all hydrogens. And those chlorines are going to have a different kind of tug and pull and force as a result of their nature. Okay? So bond energies can be very useful, but just keep in mind that they do vary a little bit, so we're going to take an average bond energy if we talk about a single bond between two particular atoms. Okay? And look at that, Model 2, now we have some average bond energies. So on average, a hydrogen-hydrogen bond is going to have a bond energy of 432. What does that mean? It requires approximately, on average, 432 kilojoules of energy to pull apart a mole of hydrogen bonds. And that's true for all of these here. Okay? And you'll notice that some of these are single bonds, some of them are double bonds, some of them are triple bonds, as we'll see as we answer these questions. So look at the bond energies in Model 2. Are the bond energies positive or negative? All of these are positive as we're talking about how much energy does it take that you have to put into the bond to break them apart. Okay, they are all positive. Do the bond energies refer to bond breaking? Well, that would mean bond breaking because it takes energy to break bonds. Positive means it's going into the system, into the bond to break it apart. What are the units for bond energy? Kilojoules per mole. How many bonds will the energy listed in the table break? A mole of bonds. Is the bond energy for a double bond simply 2 times that of a single bond for the same atoms? And we're going to provide 2 specific examples. So let's see if we can find a single and then a double. And we've got 346 and 602. And so the answer is no, it's not exactly twice. Okay, it's not exactly twice because a carbon-carbon is not going to be 2 times. It's not 2 times a double bond with carbon and carbon. Okay? Explain how to use this information in Model 2 to determine the change in energy when a mole of CH bonds is formed rather than broken. Well, if you want to find out how much energy is released when a CH bond is formed, you are just going to take the opposite value of that magnitude right there of 411. So 411 kilojoules per mole to break apart a carbon-hydrogen bond. Therefore, if you have a mole of carbon-hydrogen bonds being formed, you're going to have 411 kilojoules released, and we denote that by using the negative sign. Negative sign tells us energy is being released. That's exothermic, remember. Because the environment surrounding a bond in a molecule alters the bond energy slightly. Remember, we just said this in the little reading portion there. The environment surrounding a bond is going to alter that bond energy slightly. How do scientists then calculate one bond energy value for the table up there in Model 2? Well, as we kind of alluded to, they're going to take the average of a whole bunch of different scenarios. So you're going to take different bonds, maybe you measure how much it takes to break a whole bunch of different carbon-hydrogen bonds in different molecules, and then you're going to take the average of all of those in order to get one value that kind of represents the bond energy for that particular bond. Alright, in Model 3 we're looking here at a diagram that is showing us the net energy change for a reaction. And let me just walk you through this because it's a little complicated maybe at first. But here we have reactants, then a reaction occurs, and you have products that are formed. So this is over the passing of time. And here we have energy. Over here at this side we have energy. As you're going up, you have increasing energy. This would be high energy. This would be low energy down here. And we're going to see what happens over the course of a reaction to the energy level of reactants, products, or in between as this reaction is occurring. So basically what we're saying is before the reaction occurs we have reactants. So here in this box we have these reactants, nitrogen and hydrogen. And they are at a particular energy, a potential energy level, meaning that they are storing energy in their bonds. A certain amount of energy is stored in those bonds right there, and in order for us to get that energy out, we're going to have to break them apart. So if we want to break those apart, then it's going to require energy. We've got to pour energy into this here. Energy's got to go in. So that means the energy for this system is going to go up because we just introduced a whole bunch of energy. How did we do that? Maybe we put it over a flame, okay? Or we have some other type of energy source, electricity. Something's got to introduce some energy in order for these bonds to be broken. Okay? We got to break the NN bond here, and we got to break the HH bond there. And we have how many of them? We got 3 of these. And we got 1 over there, or 1 mole of the NN bonds and 3 moles of the HH bonds. Okay? So we break them all apart. That's going to require energy. Now we've got increased energy. Now we're at a higher energy position. And we've got 2 separate nitrogen. These have been broken here. Now they're separated. 2 separate nitrogen atoms, or 2 moles of nitrogen atoms. And all of these bonds have been broken. So we got 6 hydrogens, 6 moles of hydrogens, if you will. Now they're at a higher energy level though, and they'd rather not stay there. They're going to be happier if they can get rebonded back together with something somehow, and if they can, they'd like to even get to a lower energy position than where they started. So they're going to rearrange themselves in a new formation and form a new compound. That compound actually is going to release energy as those bonds are formed. So during this process here, when you take these 2 nitrogens and 6 hydrogens and they rearrange themselves into ammonia, like this, now they've formed new bonds, and those bonds, when they're formed, releases energy. And actually it releases so much energy that it drops even further down than where it started. This energy position for the ammonia, the 2 moles of ammonia here, actually the bonds here are storing less energy, have less of a potential energy than the original bonds of the reactants. So it even drops further down and it's more stable. That's why nitrogen and hydrogen like to form ammonia if they can, because they drop to a lower energy position and they're more stable as a result. And we compare where they started and where they ended and see that there is a drop in energy. So this change right here between where they started and where they ended is called the delta H. That's your change in enthalpy, change in heat energy. And if there is a drop, that means heat was given off altogether. That the net result here is that heat was released from this reaction. If you end up higher, let's say this NH3 here was actually higher than where you started, that means net-wise you've got to put energy into this in order for that reaction to occur. All right, it's a lot of information. Let's walk through the questions here and see if we can maybe process this a little bit more deeply. Right, the overall reaction, we've got N2 plus 3H2 yielding 2NH3, and this is balanced for us. The y-axis is your energy, and does step 1 represent a bond breaking or bond forming? We're going to break bonds here in step 1. Step 1 arrow goes up because it requires energy. You have to put energy in. That is endothermic. Okay? This is going to require energy for you to break those bonds. So now you just increase the energy, the potential energy of those particles. Okay? Draw a Lewis dot diagram for every reactant molecule. So I did that kind of up here, but I'll just draw it for you. So nitrogen, there's hydrogen. Nitrogen, you've got 5, and you're going to have actually a double bond here, I think, with nitrogen. So you're going to have, nitrogen has 5 valence electrons, so it's a total of 10. And we've got 4. Oh, I think we're going to have a triple bond here, actually. Okay, sorry about this. Let's erase that. Let's erase that. There we go. All right, so now we got 6, 7, 8, 9, 10. We got 10. We have a triple bond right here. This is a triple bond in between the two nitrogens. This is a single bond. Okay? Now, let's see what happens here. Use the bond energies in Model 2 to calculate the energy needed to break apart the 4 moles of molecules in step 1. Why do we have 4 moles? We've got 1 mole of nitrogen, 3 of hydrogen. Let's look back up here in our chart. Here's our triple bond for nitrogen. It takes 941 kilojoules per mole. And for hydrogen, it takes 432 per mole. So 941 and 432. 941 and 3 times 432. Okay? That's how much energy it takes to break apart that nitrogen, that mole of nitrogen, and the mole of hydrogen. Product, NH3 is going to look like this. That's the Lewis dot diagram for NH3. We have 3 bonds of NH. We have 3 NH bonds. So let's look up here. NH. There we go. 386. We got 3 of them, and in each of the 2 moles. There are 3 bonds, but we got 2 moles of this. So we've got, we've got 3 of these, but we have to multiply that by 2 moles. So we have actually 6 of these, 6 moles of these bonds. 6 times the NH bond, and I forgot what the number was here. It was NH 386. Okay? So 6 times 386. And what we should see here is, well, let's continue with the questions. Use the bond energies in Model 2 to calculate the energy that is released to form the 2 moles of molecules in step 2. So basically, this is the amount of energy. This calculation is telling you how much energy you've got to put in to break the bonds. This value right here is the amount of energy that is released when these NH3 bonds are formed. So what's going to be the difference? Well, you got to find out how much is released by comparing these two. Okay, so this is breaking of bonds, and forming bonds. You're going to subtract those two values. So you can take the 6 times 386, 6 times 386, and subtract the 941 plus 3 times 432. Okay? That will tell you how much energy is released. That'll give you this number right here. That'll give you that number right there, the difference between where you're starting and where you're ending. Because the first number you're finding this amount right here, and the second calculation you're finding this amount right here, and the difference between those is going to tell you how much is released. Okay? The heat of a reaction, or change in enthalpy of a reaction, is the net energy change in the reaction. Consider where delta H is located on Model 3. Discuss with your group how your answers to questions 16 and 18 could be used to calculate the enthalpy of change for the reaction Model 3, and then do the calculation. Alright, so we did this right actually up here, okay? What they're getting at is the difference again. So they're just saying that if you take these two values and you find the difference between them, you will find out then the heat of reaction, or the change in enthalpy, this delta H. Okay, as I just said, you're going to find this delta H right here. By the way, I didn't calculate this, but when you do, this forming of bonds, you can represent that with a negative value. Okay, so this would be a negative, if you want, negative 6 times 386, because when bonds are formed, energy is released. And then the breaking here, this could be positive, so you could write it this way as well. 432. Okay, so again, it's just the difference between them. Forming of bonds is negative, breaking apart the bonds is a positive energy, and the difference between those then is going to give you your net change. And since the product energy is lower than the reactant energy, you actually are releasing energy, and this should be a negative number here. Okay, this should be a negative number. The way I did it up here, actually that would have been a positive number, but I would have to say that this is how much is released. Okay, if I got my number up here, that's a positive, but I know that that's how much is being released because I know that it is an exothermic reaction. Okay? Alright, moving on. Let's look here. It says read this, so let's go ahead and read it. The diagram in Model 3 suggests that the production of ammonia from its elements occurs by breaking the element molecules into single gaseous atoms and then recombining them into ammonia. So we break apart the molecules and then they reform into something different. Okay? So, in actuality, very few chemical reactions occur in this manner. The production of ammonia does not happen this way. Lucky for chemists, it doesn't really matter because the enthalpy is a state function, which means that the actual process or pathway by which the reaction takes place, it doesn't matter. It doesn't matter how it gets there, just as long as it gets there. It doesn't affect the net energy change. Okay, we don't really care all of the changes and reactions that occur at the molecular level. We're using just a model to represent it, as long as we get there at the end and can calculate the net change. That's really all we're concerned about at this point. Therefore, it is perfectly all right to imagine that the reaction occurs as illustrated in Model 3. The enthalpy change that is calculated will still approximate the real-life reaction, because for a state function like enthalpy, only the beginning and the ending needs to be known to find out what we're looking for. Okay, so that's just a little bonus material there for you if you were curious. Balance the following reaction. Let's walk through this together. We have CH4, O2, producing carbon dioxide and water. Do you recognize this as a combustion reaction? You've got a hydrocarbon. Here's your hydrocarbon burning in the presence of oxygen, producing carbon dioxide and water. Always carbon dioxide and water. Okay? And we have to make sure we have the same number on both sides. I see I have the same number of carbons, but I've got 4 hydrogens, 2 here, so I'm going to double this. That gives me 2 oxygens and another 2 here. So that's a total of 4 on the right, so I'm going to have to double this to get 4 on the left. Okay? So it's CH4 plus 2O2. Remember, oxygen is diatomic. Yields carbon dioxide and 2 moles of water. Draw a Lewis dot diagram for every reactant and product. So CH4 looks like this. Okay. Oxygen is oxygens that are bonded together. So 12. So oxygen has 6 valence electrons. So there's going to be 12 valence electrons in O2 molecule. There are 2 there. And if I put the other 12, I'm going to have to share a little bit more here. Okay? Because if I put 12 here, there's an octet around both of them. I've got more than my valence electrons. 2, 4, 6, 8, 10, 12, and then in the middle there's a bond using 2 valence electrons, 2 electrons. I've got actually 14 represented there. I can't have more than that. Okay? So what I need to do is I need to do some sharing. So in this case, I have too many, so I can't really have one of these pairs represented. So this pair here is going to have to come in between and be shared and not be just localized around the left oxygen. So now it's really going to look like this. If I get rid of this guy, get rid of this guy, I've got a double bond in the middle, and each oxygen has 2 lone pairs. Everybody's happy because they've got an octet. Okay, and I've got my 12 valence electrons represented. Carbon dioxide, there's my skeleton structure. Carbon has 4 valence electrons, each oxygen has 6. So 6 times 2, that's 12, and another 4, that's 16. I've got 4 represented, so I'm going to need another 12. And if I just put them around the oxygens, the carbon's not going to be happy. So I know that I'm going to have double bonds there in order to satisfy the carbon. So that is actually now, I have 2, 4, 6, 8 represented. And again, I need my 16. So I'm going to put 8 more. 1, 2, 3, 4, 5, 6, 7, 8. Like that. Everybody's got an octet. And water looks like this. I'm sorry. It's 2 oxygen, or two hydrogens, 1 oxygen. Okay, that's one you probably could just memorize, and because it's so popular. Okay, so let's see what we have here. We're going to have to find the number of bonds in all this. We've got 4 carbon-hydrogen bonds. 1, 2, 3, 4. 4 carbon-hydrogen bonds. And then we've got 2 of these double bonds here. We've got 2 of these. Over here in the products, we've got 2 double bonds between carbon and oxygen. And we've got oxygen with 2 oxygen-hydrogen bonds, or hydrogen-oxygen bonds. Okay. Now let's look at the coefficients though. Inside, I wrote 2 double bonds here because of that coefficient. I didn't take this coefficient into consideration though. This 2 is a result of the molecule having oxygen bonded with 2 hydrogens, and it also is 2 moles of that. Okay, so basically we want to find out how much energy, what's the change. You are going to find the amount of energy that takes that is released when these bonds are formed, and then compare it to the amount of energy needed to break apart those bonds. So we're comparing right side and left side. We're seeing which one is bigger. If the amount of energy released is larger than the amount of energy needed to break apart, then it's an exothermic and energy is going to be released. If the opposite is true, then it's endothermic and energy has to be poured into this. Net energy goes into it in order for it to occur. Okay? So you're going to take 4 times plus 2 times something minus these bond energies over here. That's going to be a 4 there, 2 times 2. Okay, and then I just look up my energy values here. Carbon, hydrogen, double bond of oxygen, double bond with carbon, oxygen, double bond with oxygen, hydrogen. So carbon, hydrogen, 411. Drop that in there. My double bond with oxygen, double bond with oxygen. Here it is, 494. Drop that in there. My double bond with carbon and oxygen. Carbon, oxygen, double bond, 745. And my single bond with oxygen and hydrogen, or hydrogen and oxygen, there it is, 464. Okay? If you do this calculation, again, this is bonds that are broken minus bonds that are formed is going to give you the delta H, the enthalpy of the reaction, the change in enthalpy, the enthalpy of this particular reaction that is occurring here. Okay? Key point, why are the changes in enthalpy calculated using average bond energies considered approximate values? Simply because we're using average bond energies. We're not taking into consideration what kind of molecules these are in. Okay? Because we're using the average, and so we have to consider these to be approximate values. Extension questions. Here in Model 4, we're looking at a carbon-carbon bond versus a carbon-carbon double bond. And we have a diagram here. Let me just walk you through this and kind of explain what's happening here. Again, on the y-axis, we have energy. Going up is increasing energy. And here on the x-axis, we have distance. What that means is, how far apart are the two atoms? So are they real far apart? Are they getting close together? Are they really close together? Are they smashed together? How far apart, the distance of the two nuclei of our atoms here. And these are 2 carbon atoms. Okay? So notice that when the 2 carbon atoms are far apart, that we're at this energy position here, which is kind of neutral. Okay? And then as they get closer together, the potential energy is going to drop. Remember, the reason that bonds are formed is because they like to form bonds if they can get to a lower energy position. Atoms by themselves, atoms of pure elements, rarely like to be by themselves, because if they form bonds with other elements, they actually are at a more stable position, a lower energy position. So notice that the energy here drops as this bond is formed, as these come closer and closer and closer together. But if they get too close, if you push them and smash them real close together, the protons in those respective nuclei are going to repel. So if you push them too close together, as is the case here, then they don't like that. It's like, no, that takes too much energy to try to be that close. Okay, I need my space. So there is a perfect spot right here where they get to the lowest energy position. That lowest energy position is the distance that they would stay apart from each other and form that bond distance. Okay? Notice this double bond puts them even at a lower energy position. Like, wow, we could really become very stable if we could form a double bond. We get to a very low energy position. But don't push this close together because that's uncomfortable. Okay? So it shows the change in potential energy as a function of the distance between two atoms as they approach each other to form a bond. What two bonds do the graphs represent? We've got our single bond and our double bond. What happens to the potential energy of the atoms as they get closer to each other and form a bond? The potential energies drop. Okay? And they drop because, why? They're becoming more stable, forming a bond. Energy is released. Remember, a bond, energy is released when you form a bond, okay? You've got the proton from one nucleus attracted to the electrons of the other atom, and the protons of this nucleus attracted to the electrons of this one. But if you get too close together, then there's repulsive forces between the nuclei, the protons and the nuclei. Okay? Does this difference in potential energy cause a release of energy? Yes, it's going to release energy as they get closer together, but if you get too close, then the energy shoots up. Okay? What happens to the potential energy of the atoms if they get too close? Just mentioned that. If you get too close together, then you've got repulsive forces taking over, and it takes too much energy to try to keep them that close, and they're going to back up a little bit. Okay? So you don't want to push them too close together, otherwise that's going to be having protons push against protons and repel the two atoms. Okay? You have repelling protons. Compare the two graphs. Which bond, single or double, will release a larger amount of energy when it forms? And that would be the double. Look how far down it goes compared to the single. All this energy is released. If you can get way down here and form that double bond, it's so stable. And stability means it's hard to pull apart. A double bond is really hard to break compared to a single bond of the same two atoms. Okay? Which bond we have a larger average bond energy? That would be the double bond. And which bond has a shorter bond length? Shorter bond length simply means that they're closer together, because the double bond is going to be sharing more electrons and is going to then pull those nuclei closer together. It can be harder to pull them apart, harder to break that double bond. Okay? All we have to do by looking at the graph is see that here we have a drop in energy. The drop in energy is much more dramatic here with a double bond, meaning that this bond here is at a much lower energy level. So if you were to try to go and reverse this whole process, look at how much energy you have to exert. You have to get back up to this position in order to break these apart again. You have to exert all of this energy here compared to just this amount of energy for a single bond. So this is a much stronger bond. The distance between these two, the two nuclei here, is much shorter. They're much more compact as compared to the single bond. Okay? Alright, that was just a little bonus material there as we talk about bond energy. We talked also a little bit about bond length there and comparing double bond and triple bonds. Okay? Alright, I hope this one was helpful. Great job today, and we will see you as we move forward.